There we go. Alright. Find integrals involving E, identify properties of integrals, and find the signed area under the curve. This is 11D, 11E, 11F. Okay. So, first thing, 11D is all of this. That's it. Right, super easy because E is one of the best things that ever exists in calculus. So, if we're integrating E, right, if I've got E to the kx, if I was to derive that, what would I get?
E to the
K e to the kx, right? It's a beautiful thing, it repeats itself. So if I was to integrate it, it should be essentially the reverse. So I get 1 over k e to the kx, because if I derive this, I'll get rid of the c, obviously. The k comes down, cancels out the other k, beautiful. Lovely little thing. That's the methods thing. This is the more general statement. It shouldn't come up in methods, but every once in a while it'll come up in the textbooks, but I don't think it can come up in the exams. But just to cover our bases, just in case we hit the 0.5% of the time, yeah, if you've got the derivative of the power out the front and you want to integrate it, then that just comes back, which hopefully makes sense. If you derive this thing, well, the derivative of this would have to come down the front. Cool? So, for example, we've got e to the 6x. If I integrate that, what should I get? 1/6. What's that? Beautiful. That easy. Right, super easy. Lovely function. Cool. This guy, a little bit more fiddly. Okay, so e to the x squared definitely should turn up. Plus c should turn up. Does this derive back to that? No, what's missing? Right, this thing would derive to 2 times this, yeah? So what do I need to do to this? Half it. Cool. That's terrible, so let's try that again. Cool. We're going to do more of those sorts of ones where the integral doesn't immediately spit out. You have to do a little bit of work. We'll do more of those later, but for now it's just the basics. Go. Brilliant. So that's 11D. 11E is going through the properties of, well, technically definite integrals, but I'll just say integrals in general. So I've got some function integrating from A to C. Right, I'm going to, for simplicity of imagining, we'll say that A is less than B is less than C, just so we'll read A, B, C as we go across. They could be negative, they can be in a different order, but it's just easier to conceptualize if you go A, B, C. So if you've got an integral from A to C, I could split that up into 2 integrals, going from A to B, where B is somewhere in between them, and then B to C, which makes a fair bit of sense. Yeah. Cool, if I integrate something from A to A, unsurprisingly, I get 0, because if I have a vertical line, the area, well, that's 0, isn't it? So you end up with 0 there, which starts to create problems when you think about it for probability, but we'll get to that later. Cool. If I'm integrating something with a scalar multiple, so just some k, some multiple of a function, I can bring that out the front, because this doesn't vary with x, so I can just bring it out the front. Right, and that's handy for when this is particularly a terrible number. Right, you can just bring nice multiples out the very front to begin with. If you've got an integral that has 2 functions in it that are either plussing or minusing, don't take that literally as a plus and minus, just a plus or a minus. If they're adding or minusing in the integral, since integration is linear, then we can split it up into 2 separate integrals. Okay. Yep, great. I think we did this last year, but I can't remember for certain. If I'm integrating from A to B, I can think of that as the negative version of B to A. So if you flip the terminals, it's just the negative result. So you're just reading it left to right, but if you read it right to left, then you get the negative result. Cool? Yep. In 11E, it just gets you to apply a whole bunch of those. It'll deliberately ask mildly annoying versions of things, and then you just use those properties to turn it into something easier. Cool. The real crux of today is finding signed areas under a curve. I have this curve. It's not very curvy. What does it look like? Cool. We specifically where?
Through y equals
Okay, y-intercept of 2 and x-intercept
-2.
-2. So we've got 2 here, -2 there. Brilliant. We are now going to ask different things. 0 to 2, -2 to 0, 2 to 4, -4 to -2. That's the x, that's the x, that's the x, that's the x. Okay. Can we calculate that?
Yeah.
Yeah? Do you want to do it yourselves or do you want to do it together?
Together.
Together?
Plus together.
If you want to do it yourself, feel free. Cool. Alright. Well, I want to integrate this thing. What do I get if I integrate it? So, you want to integrate that? What do I get? Half x squared plus 2x. Right, so normally I get plus c, but if I've got that,
Yeah.
cool. I'm going to do this. This is one of those times where if I do the line just there, it's not abundantly clear if I'm just talking about the 2x or the entire expression, so I'm going to do it like that. Cool, okay. Say again. Pi onto, oh, plug into, sorry, I think I said pi onto, I was like, where did pi come from? Okay, beautiful, okay, I plug in 2, what do I get? 6, are we okay with that? Yep, go, minus 0, 0. Cool, so we get a nice fat 6. Beautiful. Okay, fine. Okay, what do I get for this? -6? 0? Okay, this is problematic if we're already getting different numbers. Okay, so we're going to have the same thing just between 0 and -2, right? So, put in 0, get 0. Put in -2, what do I get? Okay, let's do this bit by bit. -2 goes into that, I square it, I get 4. Half that, I get 2. Right? -2 goes into this, I get -4. So overall, I get -2. Yeah? Minus -2. Okay? Is it possible to drop negatives in this very easily? Yes. Do things carefully. Okay. And this is obviously a nice, simple curve, right? So, highly, highly recommend. Write things down. Cool. Next guy. Sub in 4. What do you get? 16. Okay. Cool. How'd you know it was 6? We did it before. Good. Kinshuk. Looking for shortcuts. I like it. Alright, we had a 2 there, we had a 2 there. The ends are going to be the same. It's the same function. Cool. We get 10. Beautiful. Fine. Next guy.
-2.
Cool. Using that from before, we had -2.
0.
Okay. So I heard 0 and 12. No apologies.
Oh, wait, yeah, no, it's not. Wait, is it?
Your guys are calculating. Cool. -4 squared, 16 half is 8. -8, yeah, 0. Okay. Okay, so we've got a whole lot of values. Fantastic. Maybe we should color these. Let's color these regions. Okay, 0 to 2. Do they go up to 4? Yes. It's supposed to go up there. This is going to be 4. No, it's going to go up to this. Sure, it's only 4, 2, 0. Obviously, -2 don't go any further left. Cool, those aren't threes, those are squiggles. Okay. Do those results make any sense?
Yes.
Yeah, okay. The one that I'm most interested in is the bottom one. What's negative? The area is negative? Okay, let me ask you this question. How big is the red area? 2. Right? That area is 2. Right? However, when I do an integral, or a definite integral for it, I get negative 2. Right? Now, why do I get a negative area as an output? Right, because it's considering this as, okay, my width is 2 and my height is negative heights. So I should get negatives, right? Be careful. Right? If it asks you what is the area under the curve, you should always get a positive result. Right? It might be that the math spits out negative and then you have to flip it. That's fine. But be very careful about how the question is worded. If it just wants, tell me what this integral is, that's fine. You can spit out negatives all day. But if it says, what is the area under the curve, now you've got to think it through. To highlight exactly that, let's take this, and I'm going to say I want the area between this function, the x-axis, x equals negative 4, oh, x is an element of negative 4 to positive 4. Let's say I want that. Cool. What might be your first attempt at solving that? Okay, integrate might be your first thing, okay? So integrate between negative 4 to 4, okay, of this function. So we're saying that? Cool, okay. What do we get? Four gives us whatever it is. What's this? 64 on 3. Yuck. Minus 16. Minus negative 64 on 3 minus plus 16. Is that what we get? Yep. So we've got 128 on 3 plus 30. Sorry, minus 32. Is that right? Yep. Which is on 3 is 96. Gives us 4 onto this is 32 on 3. There we go. So we're saying that the area contained by this curve and the x-axis going out to the positive and negative 4 is 32 on 3. Cool. That is right. All the math that you've done there, everything in red is consistent. But red doesn't actually answer that question. Okay, so let's draw a picture first. What does this look like?
It's a parabola.
Parabola? Yeah, there we go. That's better. Yeah. Cool. Specifically, where am I crossing?
X negative, y equals negative 4.
Okay, y is negative 4, yeah, and right, the 2s, there we go. So it's there and there, so that's 2, that's negative 2. Something like that. Back, okay, so that's there. Yeah, there. Terrible 2. Cool, alright. What is this question asking me for?
Area between.
Area between
On the x-axis.
on the insides, alright? So I want, let's call these, we'll give them different colours. Let's see. happy that we're after A, B, C, and D?
Yeah.
Right.
What is the radius?
Sorry.
What is the radius?
What is the radius? Alright, no. Don't worry about the red yet. Don't worry about the red. We'll get there. Right, let's try to set this up. So, is my actual question asking me for A plus B plus C plus D? Is that what my question's asking me? You do think so or don't think so? You don't think so? Okay, what's wrong with it? It's minusing the negative areas. Okay, so I want what these are. However, I want them as absolute values. Yeah. I could absolute everything, but these are already positive. Yeah. So I could write it like that, but in methods we don't typically deal with absolute values. So how else could I deal with it? If I know these are negative to begin with, what do I do? Right, minus them instead. Right? So I just change this to A plus B minus C minus D. Okay, great. Well, let's start this up. That's negative 4 to 2 of... Actually, I'm just going to shortcut this and just write alphabets. Therefore, negative 2. That's a 0 over 6. Is that clear? Where's this? 0 over 2. Yeah.
How do you find the area between 0 and 2 and 2 to 4 and times by 2?
Perfectly valid. Right? You can exploit symmetries all day long. That's perfectly fine. Okay, so we've got this. Great. Now, if you want, you could have written A minus C minus D plus B if you wanted to keep all your terminals in a row. That's fine too. Right? There's a whole bunch of different ways. As Kinship just said, if you wanted, you could figure out B minus D and then times by 2 because these are clearly the same, these are clearly the same. So I'm going to do that now and just say since A equals B and negative D equals negative C, then we can shortcut all this. Negative 4, negative 2. Oh, do we want to do that one? Yeah. Oh, yeah. Actually, I was going to do this even better. Would you rather calculate A or B? B. Right, no negatives, yeah? So these two together become integral 2 to 4, 2 lots of x. Yep. And would you rather calculate C or D? D. So we've got minus 2 lots of 0 to 2. That's the x. Beautiful. Cool. And now we can start to actually calculate what we're doing. So we've got 2 lots of integrate over this, what's that? 1/3 x cubed minus 4x. Is it 4x? Yeah. Between 4 and 2 minus 2 lots of 1/3 x cubed minus 4x between 0 and 2. Okay. What do you got? Okay, is this less straightforward? Yeah?
Yeah.
Okay, then we'll do it bit by bit. So, 4 cubed. 64, okay, so we've got 64 on 3 minus 16. Okay, we're going to deliberately do some things. Okay, cool. Okay. Okay, are we happy about that? It shouldn't be.
Yeah, it's like for actually times the first one by 2.
Right. Because I've got these 2 multiplying that whole thing.
And the second one really doesn't matter.
Second one, it doesn't matter because it's a 0, but it should be like that if we're doing things properly. Cool. Be careful about your brackets. Right? Every time you make one of these nice shortcuts, you open up another way that you can stuff it. So just be conscious and careful. Beautiful. From there, can we do anything interesting? How about this? You've got 2 times all this, right? That's unique. But this is not unique. That repeats itself. So I've got -2 of these minus 2 of these. Right, so I've got -4 of those. And then this is just whatever this is, 128 on 3 minus 32. Yep. From the space, it'll come up here. What have we got? 128 on 3 minus 32. Since everything's going on 3, we might as well do it now. 96. What's this? Minus 4 is minus 32 on 3 is plus 32, which is another 96 on 3, I think. Yeah. Cool. Bang, bang. 150, 160 on 3. Is that what you guys get? Yes? No?
Is the 128 on 3
Is the 128 on 3
minus 32?
minus 32? Yeah. What about it? Where is it up here? So 32, I changed it to 96 on 3. It's minus what? That's this. Cool. So we're all okay? Yep. Beautiful. So we get that. This is most certainly not equal to that. What happened? Yep.
Basically, you had the negative version of the problem, so they cancel out the problem.
Cool. Okay. How could we confirm if our theory about what went wrong is correct?
Direct minus the C and D and
Graph the that has a negative there.
Say that again.
Graph the function.
Graph the overkill. How about we just figure out exactly what C was for a second? Where was that? That was, oh sorry, C and D was all of this bit. Not red, I think something else. We'll go, is that? This is this, that's pink. Yep, so this is C plus D, which ends up being whatever it is, 64 on 3. Okay, so this is 64 on 3. I'm thinking that I've taken that away from what the result should be. So if I add 64 on 3 to that, should that make it correct?
That should make it,
it would get.
Does it though?
it should make it 128 on 3 minus.
Right, 128. Why 128? Right, because what I did was I minused this when I should have added it. So that I'm twice as far away instead of once as far away. Also, this, if I go 32 on 3, add 2 lots of 64 on 3. Cool, I've got 32 on 3 plus 128 on 3 equals whatever this is, 150, 160 on 3, and they match. Hooray. So that is where our problem was. Cool. What's the lesson?
Be conscious about what you're doing.
Be conscious about what you're doing. That's a general good advice for life. Specifically when it says find the area between the x-axis and this function, between some endpoints, what should you probably always do? Sketch it. Right? Do you have to sketch it perfectly? No. What do you only really care about? Which intercepts?
The x-intercepts.
Just x-intercepts. Right? So you don't actually care about what it looks like really, you just care about when is it positive, when is it negative, and specifically where does it cross over. Cool? Because I could give you potentially something that's just la di la di la di la la la, right? You don't have to sketch the whole thing. All you care about is when these crossover points happen.
That would be a very kind of.
Yeah, it's a bit of pain in the ass, but like in theory, right? In principle, rather. Right. Those are the only points you really care about, and that it's positive or negative, and that's all you're done. Be conscious that you could get something that does that. So you could have an x-intercept, but it doesn't actually flip over.
Yeah.
So in this case, this is negative, this is positive, this is positive. You only really care about this one being negative, and then the rest you're just gonna.
Oh, that one.
Right? Yep. It's physics. How many times do you have to find the area in the graph in physics? Yeah?
That's fair.
Yeah. Like there's heaps of other things as well, but that's the one that you've already done. Cool. So yeah, takeaway lesson is whenever you have to find an area, unless you are 100% sure that it is always positive or always negative or something, right? Draw a quick sketch, just double check, and if there is definitely x-intercepts, draw the bloody graph. Even if you know exactly where it is, draw the bloody graph. Because the number of times you'll drop a negative doing something dumb way outweighs how many times you'll do it perfectly. So just always do a little thing, set yourself up, write a general equation like we did here. Like this is hardly complicated, right? Just set yourself up, then just progress through. If you can find symmetries and things to exploit, great. That makes life easy. Write the basic thing first just to make sure. Cool. So that's 11F. 11D and E are pretty quick and easy. 11E just gives you a whole lot of symmetry lessons, so that when you see them later, you're like, oh, I can exploit that. It just makes life a bit quicker and easier. 11D is just the integrals with E, super short, super easy. Questions, queries? No, we're all good? Cool, how about it? Yeah.
So if you want to find the area between classes,
You can do it that way, yes, but that's going to move outside of yes. So then you would, the easier way of doing it would be to invert the function. Just Jackson line, and then you just do cross the x again. Right, but it depends what your function is. So if your function is invertible, then you could invert the function and then do just integral across the x. But if the function, so say you have, and they do this in spec. Say you have that, and you want to know that area. But if this was a perfect symmetrical thing, then you could just go, oh, I'll just find the integral of this and times by 2. But if it wasn't perfectly symmetric, then you'd have to go, all right, say this is f of x, right? Then you'd have to switch it into f -1 of x, which is, I'm going to call g of y, right? And then you integrate g of y with respect to y between I think I've got that the right way around. Yeah, I think that's right. Yeah, cool. But that's not in methods, so you don't have to worry about it. Cool. Okay, bye-bye.